Hello, everyone. Welcome back. I wanted to talk to you today about I think, a very interesting problem that can be looked at in a number of ways, or at least in a couple ways. It's found in the textbook College Physics, 11th edition, Volume 1. Surway and Buell are the authors. It's an example problem that they have in the textbook on pages 179 to 180. Basically it's the Surway book that, as I'm saying this, is the book that's currently used for Physics 120 at our school, non-calc treatment. But anyway, this is where it is for future reference in case books change and circumstances change. It is a very, very good rocket problem. A number of ways you can look at it. I mean, at least of the two ways I'm thinking right now, I can bring calculus into the whole matter. Again, I'm not expecting that for the non-calc treatment that is being offered for the non-calc class that is being taught for physics, the Physics 120. You don't have to know it, but it's good to know if you have a little bit of a calculus background to kind of see the ways that this can be looked at. The book does a great job, on this example problem, as I say in the notes. So whenever in doubt, please follow the book very closely. I have this document, so to speak. I have it on Canvas that goes into all of this as well. As with so many other things, I try to put them on Canvas as well, guys. Part D of this example problem that I'm about to do, guys, had the potential to create the greatest confusion. So let's look at it. Let's look at it some. Before we go there, let's say a couple things about what they already have, and we'll kind of take it from there. They talk about the example problem from Chapter 6 is example 6.9. It's called single stage to orbit, SSTO, type of rocket problem. And what they're saying is essentially this. A rocket has a total mass of 1.0 times 10 to the 5th kilograms and a burnout mass of 1.0 times 10 to the 4th kilograms, including engines, shell, and payload. So in other words, the total mass at the beginning of the whole thing is 1 times 10 to the 5th kilograms, and the burnout mass, the mass at burnout, is going to be 1 times 10 to the 4th kilogram. The rocket blasts off from Earth and exhausts all its fuel in 4 minutes. Burning the fuel at a steady rate with an exhaust velocity, VE, is 4.50 times 10 to the 3rd meters per second. They've got A, B, C, D here, guys. A, for questions, A, B, C, D. A, if air friction and gravity are neglected, what is the speed of the rocket at burnout? That's A. B, what thrust does the engine develop at liftoff? C, what is the initial acceleration of the rocket if gravity is not neglected? So gravity kind of comes into play here. Later on, they're going to say, have it come into play. What is the initial acceleration of the rocket if gravity is not neglected? D, estimate the speed at burnout if gravity is not neglected. So for C and D, what is the initial acceleration of the rocket if gravity is not neglected? And D, estimate the speed at burnout if gravity is not neglected. So you got to remember, you're fighting gravity the whole time. We're going to assume there's not going to be a variance in the G. The gravitational field G is going to stay the same, 9.81 meters per second, or 9.8 meters per second, but it's going to stay, it's not going to vary for our purposes right now with all that's going on here. That's Occam's razor. They want you to pretty much assume something like that. So A, let's see what we got here. Calculate the velocity at burnout, ignoring gravity and air drag. So the essential situation, you guys, is we know certain things just looking at the book, some of the formulas that are there, and we'll see what we can say about how fast something goes. Remember, there is the idea that delta V of the rocket is going to be V of the exhaust times ln of the ratio initial mass of the rocket and final mass of the rocket. It's going to look like that. The way that plays out is I'm using a little slightly different, somewhat slightly different notation than what they're using in the book, but or how they're answering it. But it's trivial, like capital R here, capital E here, that kind of thing, you guys. Let's see what we can say. If this is the case, we agree this is based on previous work that we've done and notes that you have on Canvas, how I show how to do the rocket problem, how it all plays out by conservation of momentum considerations. And we've already discussed that. That's already discussed elsewhere. So we have reference to that. Okay, sounds good to me. And we said how that all played out. Remember how that all happened. I mean, it's not going to be, for those with the calc background, you're seeing how that all came about when we said that. Remember, we said there was conservation of momentum when we had, there's a lot going on. Conservation of momentum. So momentum doesn't change. So if I'm going to do dmv dt, it ain't changing. It's going to be equal to 0. I'm ignoring vector notation right now, but when we actually do this, we're finding dm dt v plus m dv dt equals 0. So, I mean, there's a lot that can happen vis-a-vis that. And I'm kind of doing this pretty cold, you guys. Now, the m is the mass of the rocket. This right here is, so you got to be extremely careful with the velocities under consideration here. Because there is exhaust going on, the exhaust is leaving the rocket at dm dt. So the v here is v of the exhaust. The m right here is the m of the rocket. And this is how the speed of the rocket changes. So that's an r for rocket, and that's an r for rocket as well. You're basically talking about a situation where d capital, and then the small m, call it capital M for the mass of the rocket, d dt. So this is the change in mass of the rocket. The exhaust is part of the mass of the rocket before it's being expelled. So you have this right here. And the other one is the mass of the rocket, whatever it may be. Now, the mass of the rocket is a varying quantity. It's not a constant. But the exhaust speed is associated with pieces of the rocket, the exhaust fuel, and then other things later on that are allowed to come off of it. The rate at which the rocket's losing mass and the speed at which the mass is being expelled, plus the mass of the rocket and how fast the rocket's going, is equal to 0. So there's a lot that can be said here, guys, when we do this. We can actually say that, get that over to the other side, you got dm dt, and I know we've done this, but I think it's important enough that when we see it, just being hit with a problem cold sometimes, dvr dt. V sub r is a variable quantity. The rocket speed change. The rocket started at 0 speed. This VF right here is actually VRF. Velocity of rocket final, velocity of rocket initial. So kind of look at it that way if you want. There's certainly a lot that you can say here. Let's multiply by dt on each side. There is a whole lot we can say here. Let me see exactly how I want to do this. Let me multiply by the differential dt on each side. and divide by a negative m. So what you have here is multiplied by dt on each side. The dt's cancel. And this is some of what's going on here. For those without the calculus background, you don't need to lose a whole lot of sleep on this, guys. You just kind of know that they gave you this in the non-calc treatment. For those with the calculus treatment, they give you more of a derivation. I think if you have a calculus background, regardless of what class you're in, it's good to look at this stuff. But you can ignore it if you don't have, like I said, if you're in the non-calculus version of the class, stay with this and stay with what they gave us here. Let me just kind of demonstrate why it's actually the case. If you're going to do something like this, a whole bunch of ways, so many things can get looked at, I guess you could say. We're looking at all this, you guys. Let me keep this up here for as long as I can. Eventually, that's probably going to get erased so I can actually full-fledged just go all the way across the board and do some stuff here, guys. As we are looking at this, you're coming to here if you've done this carefully. If two things are equal, their integrals are going to be equal. Let me integrate this from the appropriate initial mass to the final mass. Well, this is a big number, and that's a small number. VE is a constant, so take them out of there. A whole bunch of ways you could go here, actually, guys, if you really want to play this. Right, like that. And the other guy is the integral from VRI to VRF. And that's what the VF and VI are. I mean, later on we might just even be able to just get right away from that. Okay. Okay, I'm sorry, guys. I haven't even put the thing in there right. Okay, DVR right here. All right, there you go. They're being set equal to each other. Well, when you do this, right here, the integral, ignore the negative for a second. For a little bit, ignore the negative and just say dm over m, that integrated, is the natural logarithm of capital M evaluated between the limits of mf and mi. So you can bring the negative out, do the integral, you get ln mf minus mi cross that bridge in a second. Do the integral here, that's just VR evaluated between VRF and VRI. That's just going to be delta, VRF minus VRI, that's just going to be delta V of the rocket. And that's going to be way down there, guys, VF minus VI. That's kind of where they're getting that. This right here, the difference between two logarithms, is the logarithm of the appropriate quotient. Negative right here is the same as negative 1. Negative 1 times the natural logarithm of this is the same as, you could put a negative 1 right here. Negative 1 times the natural logarithm of this is leave the VE alone, natural logarithm of MF over MI to the negative 1. I brought the negative 1. The negative 1 was right here. And then from the properties of logarithms, multiplying a natural logarithm by negative 1 is the same as losing the negative 1 with which you were doing the multiplication and put negative 1 as an exponent inside of the logarithm. And this is DVR. Okay, so not done, getting close. This whole thing to the negative 1 is MI over MF, and that's where they're getting it. And that settles it, actually. Is positive MI over MF. And this is delta V. And this is where they're getting that, you guys. And that's where they're getting this stuff right here, you guys. You got this, and you got that. So, okay, just for the sake of completeness, for the sake of being very rigorous about this thing, that's how the whole thing is playing. If you're going to do the job here to actually get it there. Well, if that's the case, and I mean, there's a number of other things that are kind of coming into play here, you guys. If you really want to talk. You can also say, I mean, while we're at it, I mean, while we're in that business here, this thing right here, its magnitude, the magnitude of m times dv dt, dv dt is acceleration. Mass times acceleration is force. The amount of thrust force moving the rocket, the part of the rocket that's intact, going to where it's going. It's expelling exhaust from the back part of the rocket. It's expelling the exhaust and it's moving forward. The forward thrust associated with the rocket per se, the classic rocket that we think of being as the rocket, the thrust is going to be this absolute value. The absolute value of negative capital M dvr dt. So there's a number of ways you could do that as well, guys. You could say F thrust of the rocket is the absolute value of m dvr dt. If it's negative, just make it positive. The big thing is this, dvr dt, and that thrust, ladies and gentlemen, is equal to dm dt VE. Now people are going to argue, hey, well, wait a minute, we just said we're not doing calculus here. Well, let's not then. If you don't want to, if we're not going to do calculus here, this is the calc version of it. For those that don't need it, there's the calc version of it. What's the non-calc version of it? The non-calc version of it is simply going to be F thrust, and that's going to be equal to, you put an absolute value here. I don't want to blind us too much. Delta VR over delta T, which is the same as delta M delta T VE. In place of D's, you put the Greek letter delta, and it comes the same thing for a non-calculus look at it. That'll approximate what's going on. Yeah, it should look a whole lot like this guy. Okay? So that's some of what's happening there, you guys. So when we do this, at least we got an idea what language we could speak either language. We could talk about the language in terms of calculus, which is the best way to do it. If you're going to be very rigorous about it, we talk about it in terms of calculus, and we're getting this, and we're getting this. We're deriving this and deriving that through calculus. This right here is more of an approximation. Instead of a D, a differential elements here, you put a delta. And that's how you go there. Okay, so works for either class, you guys. The big thing here is I'm going to throw some calculus into this thing for your personal enrichment. We're going to get the right answer without calculus for all four parts, A, B, C, and D. And then I'm going to look at D and think that it's a little bit, there's perhaps more that can be said about it that might be of great use to you. All right, so with that in mind, see what we can say here, guys. We know a bunch of stuff. We have a bunch of stuff here. Let's see exactly where we want to go here. I'll erase probably a good amount of this, leave some, and we'll see. We'll just erase as we need to go. Luckily, we can always go back with the film, and we can always talk about it a bit. Okay, let's leave that, at least temporarily, let's leave that up there a little bit, what I've left here. And let's keep proceeding on this. So, they told us a bunch of stuff here. Calculate the velocity at burnout, ignoring gravity and air drag. So, again, they gave us some data, you guys. The data they gave us was initially the rocket was at rest. And this VF-VI is actually, according to other language I've spoken, VF minus VI is delta VR, the change in rocket velocity. That's velocity of rocket final, velocity of rocket initial. That could be easily written as VRF and VRI. We're not doing that. We're using their language, VF minus VI, but it does mean final velocity of rocket and initial velocity of rocket, respectively. We are told a number of things. VI is 0. They are telling us that the velocity of the exhaust, I've been using capital E. In the book, they use small e. That's not a big deal. 4.5 times 10 to the third meters per second. Uh, 4,500 meters per second. The initial mass of the rocket before anything happens to it is 1 times 10 to the 5th kilograms. The final mass at burnout, that's the way they speak it. They're not saying that much has been, they're not saying this much has been expelled. They're saying this much is left over. They're saying this much is left over. Not this much has been expelled, but this much has been left over. What is that? This is 100,000. This is 10,000. The difference between 100,000 and 10,000 is 90,000 kilograms have been expelled. From 100,000 kilograms, from 100,000 kilograms to 10,000 kilograms, that's 90,000 kilograms have been expelled. 90,000 kilograms have been expelled. Okay, well, let's see what we can say here. Speaking of the way they're asking us to do this, can we actually find the answer here? This is for A, you guys. And again, it's all fully solved in the book. Let me just, the way they got it is how you're going to get it. The way you're going to get it is you're going to add VI on each side of this equation to get VF. You're going to get VF by itself, add VI on each side of the equation. So see what we got here. Via, and that's all. And they got, like I said, the subscript small e. I kept the big E because that's what I've been using. I don't think we're going to make a big deal out of that one, guys, but let's watch this. So it goes pretty smoothly. I mean, the derivation went pretty smoothly. We got to there. At this point, you're simply going to put, I don't know what VF is. I do know that VI is 0. I do know that VE is 4,500 meters per second. That's 4.5 times 10 to the third. It is ln of 1 times 10 to the fifth divided by ln of the ratio 1 times 10 to the fifth divided by 1 times 10 to the fourth. That's just 10. This is going to be a 10. ln of 10 times this will give you the VF. And this is if there's no gravity that is cut. Let's say there was no gravity. 1.04 times 10 to the fourth and there it is. What is that? Well, it's pretty fast. I mean, it's 10,400 meters per second. 10,400 meters per second, you guys. That's if there's no gravity. For some reason, I don't know how we're going to get in a situation where there's no gravity. Well, let's say somehow these guys, this ship is in outer space, and there's no gravity anywhere around, and they were able to take some kind of space shuttle, get over to this space vehicle, get in the space vehicle, and take off. There's no gravity to deal with. That is ignoring gravity. That's the speed, 10,400 meters per second. After 90,000 kilograms have been expelled. You've gone from 100,000 kilograms that are initially present, the entire mass of the space vehicle, and you've lost 90,000 kilograms of it, and now the space vehicle that is left over, so to speak, is the crew and the remaining part of the spaceship to do what it's doing. It's 10,000. It went from 100,000 kilograms to 10,000 kilograms. Lost 90,000 kilograms, you guys, for that to happen. Okay, so that is true. That's true. They want to find out the thrust, find the thrust at liftoff for B. Okay, so far this is okay. If you go with this that I gave to you guys, if we just go with everything that they give to us in the survey book, and they don't derive it because it's a non-calc based treatment to get what we need to get. If we get to here, we're good. If we know there, I mean, the book tells us that. We just take it, yeah, that's the way it is. They gave it to us, that's what it is. Simple as that. Now they're asking, find the thrust. The thrust, there's a number of ways to go, guys. You're going to get a negative number, but I already told you we don't much care about the negative number, guys. I threw the negative number out the window. I just care for the absolute magnitude of the thrust. As far as a positive or a negative, the exhaust has a tendency, absolute tendency, to go in the opposite direction as opposed to where the rocket's going, per se. The rocket goes one direction, the exhaust goes exactly the opposite direction. That's why there's a negative there. We just want the magnitude. We already know they're going, the exhaust fires one way, obviously, and it propels the rocket in the exact opposite direction. That's where the negative comes in. For our purposes, the way they say it, just get the absolute value. Get a positive number. Okay, we know this is true, but we know that's true also. So the thrust, you guys, you could say a lot. You could say a lot. I think this is where it gets kind of interesting. This is where it gets interesting. What is the thrust? I think they're saying here, find the thrust at liftoff. So what they're trying to say here, you guys, is there's a number of ways you can be looking at this, how this whole thrust problem is going to work. This thrust is a pretty fascinating dynamic in its own right. Delta VR over delta T. Delta VR over delta T is completely analogous to dVR over dt. dVR over dt and delta VR over delta T are completely analogous to one another. This M, let's just stay here. This M, delta VR over delta T, is a constant. Yeah, it's a constant. How on earth is it a constant if the mass of the rocket will continually change? It'll go from being very massive to losing 90% of its mass. It'll go from 100,000 kilograms, and at the end, it'll fall down from 100,000 kilograms, it'll fall down to 10,000 kilograms. Its mass is initially 100,000 kilograms, and then at the end of all that, its mass is just, it went from 100,000 kilograms mass to having a mass of only 10,000 kilograms. Wow, what does that mean? Well, as the mass changes, the acceleration changes too, and the product is going to be the same. The product is going to be, for our purposes here, could this be different? Could rockets operate in a different manner? Sure. I mean, we could. There could be alterations to this in the sense that you could. I don't want to use the word accelerate. You could up the rate at which things are being expelled. It doesn't have to be a constant rate at which something is being expelled for that to be the case. It's very interesting. The rate at which something's being expelled is a constant. VE is a constant. That's a constant. That's also going to be a constant. The crazy thing about it is its mass keeps getting smaller, but its acceleration keeps getting better. Of course its acceleration is going to get better. Of course the acceleration is going to get better. Why wouldn't it get better if it has less mass with which to move? It's easier for me to accelerate a pickup truck that is empty of all cargo than it is for me to accelerate the same pickup truck that's loaded up with $10,000 worth of goods. Or maybe $10,000, 10,000 kilograms of goods, maybe worth $10,000 or much more, right? But if something's very, very massive, you might have the same thrust force, but if it's so massive, it's not going to accelerate very much. You start throwing things off that truck, and you've got that same you've got that same thrust, less mass that the truck has, the faster, the more radical the acceleration is going to be when it takes place. So these are directly proportional to each other, or inversely proportional to each other. If he gets really, really small, he gets really, really big. If you make this mass half as big, the acceleration is going to be twice as big, because it's got to be equal to a constant, and that's a constant in this case. The way they've set up the rocket, it's going to be in this particular case. It's not to say every rocket's got to be that way. There's many things that can be done. All right, so if that's the case, you guys, when they're saying B, compute the thrust at liftoff. Basically, stay with this guy because it's a constant. This guy ain't, the M and the delta V, the delta VR over delta T, the ratio delta VR over delta T and capital M, they're not constants. But when you multiply them, they're always a constant, and they're going to be equal to that. So use that one. So they kind of say that to you, and there's a lot that's maybe not said, or maybe it's just kind of implied. It is implied, definitely implied, and we have to see it. Let us talk about it then. If that's the case, the thrust is delta M over delta T times VE. This right here is a constant. That right there is a constant. That ain't constant, and this ratio is not constant. If they are inversely proportional to each other. If you were to make this mass 3 times what the initial mass was, this will be 1/3 the acceleration that it initially was. If you make this mass 1/3 the mass that it initially was, the acceleration will be 3 times the acceleration that it initially was, so on and so forth. And it is a constant. It's a very interesting constant. And there you go. So it could be, and these definitely are constants. And they're equal. These are constants. These two are not constants, but this is a constant, and that is a constant. It could be a constant answer. They're not, but they're inversely proportional to each other, so when you multiply them together, you will get a constant, always, the way it's set up here. That's a big thing, you guys. That's a big thing. I'll make a long story short. The book says it their way, I'll say it my way. It ain't much of a difference. Find the thrust, the absolute value of, I'm not even putting the absolute value notation. I know it's got to be a positive answer here based on everything I just said. What's going on here, guys? What's the thrust? Well, that's the thrust, right? Because we said that is equal to m in terms of magnitude, ladies and gentlemen. This product is equal to that. So I'm going to go here. I told you that's the easiest way to go, and that indeed is equal to that. All right, let's go right there. VE is 4.5 times 10 to the third meters per second. 4.5 times 10 to the third meters per second. Delta M, what happened here? I told you it was initially 100,000 kilograms. The initial mass of the rocket was 100,000 kilograms. The final mass of the rocket is 10,000 kilograms. 90,000 kilograms were lost. 100,000 minus 10,000, the delta M total is 90,000 kilograms. It happened in 4 minutes. 4 minutes, huh? Every minute's got 60 seconds. 4 minutes. Correct? So that's 240 seconds, 90,000 kilograms. This right here is meters per second. Trust me when I tell you it's going to be kilograms, meters per second at the end of the day. See what we can do here. Let me see some number of ways you can take this whole thing, I guess you could say. There is, that's 3 times 80. 3 goes into 90,000, 30,000 times. Let's go 30 times 8. 30 times 8 is 240. 30 goes into here, right? 30 goes into here 3,000 times. 80 goes into there, 450 over 8, which is 225 over 4. So let's see here. 225 over 4. The 4 will cancel into the 3,000 750 times. So it'll be 750 times 200 times 225. Interesting. 225, you guys. So let's see here. So you basically would go that way. So let me try to think here. Be 2.5 times 100. 2.25 times 100. 100 times 3,000 is 300,000. Let me see here. Right, 300,000. It would be just doing this in my head, guys. I kind of regret doing it now, but let me just do it. 2.25 times 300,000 is 600,000. 675,000 newtons. Let's just see if that's true. No, it's not. Okay, forgive me, guys. That's maybe it's a good idea why to keep keep this as is. Let's just make sure it is on. Okay, I got a different number on that, but okay. So the way you would do it is just do the actual mathematics on it that they got on here. For some reason, I'm not even agreeing how they're doing it, but I think there's maybe a different answer here. Trying to figure out how I would actually say this. One way to do it is just go the 240 right into here, and that's 450 over 24. That is 450 over 24, right. Take 240 into here. The zeros cancel out. You got 450 over 24. You got 150 over 8. And from there, the 8 would go in there. However many times it's going to go here. Let's have a look at it. 150 divided by 8 times, this is make sure we're agreeing. Yeah, they're definitely right. I'm wrong. They round off. That's okay. It's then they rounded off to 169. To 1.69, so I'm going to go like this when I do it. See if that's actually going to be the case on this, you guys, when we can do it. Yeah, so it's going to be coming out like this. They got 1.69 times 10 to the 6th newtons. 1.69 times 10 to the 6th newtons. We got 1.6875. 1.6875 times 10 to the 6th. Okay, they were right, I was wrong. I'm not sure how I got the answers I was getting here, guys, but there's got to be there's ways you can do this stuff in your head. Obviously, it's not my day to do it. I guess it was the 150 over 8, and then you could bring the 8 into here. It's a bit of a mess. I mean, the way you would have done it in your head, you said, okay, here's 24 times 10 is 240. 450 times 10 is 4,000. 450 times 10 is 4,500. 24 times 10 is 240. The 10s cancel. You got 450 over 24. Take a 3 out of here, you got an 8. Take a 3 out of there, you got 150 over 8. And then just for your, we do something like this. And then you say, okay, can you get an 8 into here? Well, an 8 goes into here 10,000 times and 1,250. So looking something like that. Then you're going to multiply this. So it's quite the move you got to make there on that. Just confirm. Indeed, it's the same answer. You could have done this and say, well, wow, this is what? 11. This is 11,000. I'll make it 1.125 times 10 to the 4th. That's 1 1/8. That's 1 1/8 times 10 to the 4th. That's 1 1/8 is 9 over 8. So how would that go? Well, 9 over 8, you'd go here and you'd go for it in that regard. The 8 goes into here. There's stuff you could do. It would take a while. But if you got stuck having to do this by hand, you could do it. And like I said, this right here, you're right down here. Okay. The big thing, guys, is that we can get the answer. So when we look at it, I just thought perhaps there was an easier way to do it. They write it, like I said, their answer, they approximate, and we'll go around that. They approximate. They definitely did it right. They just chose to approximate, and there's nothing wrong with that. depending on the game you're playing here. Personally, doing a problem like this, if I'm doing it on multi-levels, I probably would not go here. When I'm giving the answers, especially if there's something you're doing on, in the end, I guess you can round stuff off, but if you're doing something on some sort of exam, computerized exam, online exam type thing, typically the way I like to construct things is I tell people be as accurate as you can be, and then at the end, if they ask for a round off, go for a round off. If they don't ask for a round off, just give a very accurate answer. As such, this is more what I would write down rather than this. This is a more accurate answer if I'm entering this into an online exam or something like that. Okay. Anyway, that's neither here nor there. Forgive the digression and getting off topic a little bit, guys. But we got this right here. We can say either one. They said either one. Hey, round it. If they were to say to you, please round this round this to the nearest 10,000. Now again, the actual answer is 2,000. This is 2,500 newtons bigger answer. 2,500 newtons bigger answer than that. So okay, if it's a computerized exam, depending who's giving you the computerized exam, I basically tell people just give me the most accurate answer possible. And if I'm not asking for significant figures, nobody's asking for significant figures, don't go here. Stay here. Anyway, stuff works out okay. We got it. That is the thrust at liftoff. This is actually kind of an important thing to know here. We are going to regard this thrust right here, whichever one you want to use, and you don't need to hear me deliver another speech on that. Whichever one we are allowed to use, that thrust is the same throughout. Is the same throughout the journey. So it's not just at liftoff. It's basically everywhere. While there's burning going on, that's the thrust that's being provided. That's the push that's being given as this thing is going. So that's A and B, you guys. C, find the initial acceleration, including the gravity force. Find the initial acceleration, including the gravity force. Write Newton's second law, where T stands for thrust, and solve for A. Okay, so in all this process, you guys, that's the thrust. We got all this. Let's see what we can say here, guys, when we're doing this. Don't want to erase almost any of it, to be honest with you, but let's erase some at least, and we'll figure out where we're going to go. All right, they want to know. So that was A and B. A and B asked respectively, A asked, what's the final magnitude? A asked, what is the final magnitude of velocity if gravity is not taken into consideration? What is the final magnitude of velocity if gravity is not taken into consideration? The final magnitude of velocity if gravity is not taken into consideration is 10,400 meters per second. That's 1.04 times 10 to the fourth meters per second. What is the thrust? The thrust is 1,675,000 newtons. 1,600,000. Forgive me, no, it is, we said the thrust, so we said, just write this and have it here, at least for now. The final was 10,400 meters per second. Depends how they ask you to give an answer, guys. That's kind of just where we got to watch out a little bit sometimes, right? We got this. So we know all this. One or the other's fine on this, guys. It looks good. And the other one, the force thrust, we said was 1.6875 times 10 to the 6th newtons when we actually calculated it out, long way. They chose to make that 1.69 times 10 to the 6 newtons. Okay, one's more approximate than the other. Again, depending how they're asking you questions, guys, depending what you're asked to do. If you're asked to round something off, go ahead and round it off. If there are no significant figures that are going to be playing a role in this whole process, then give your answer as accurately as you can, because you may have only a 2% error margin that's allowed in the computerized system, in the online system, a 2% error margin. And they're not bringing in significant figures into account. If that's the case, then go as accurate as you can. This is a better way to write it. If that's the case, just to cover yourself. Okay. But they also said that. Okay. The other one is saying, well, what is the acceleration? What's going on here? Acceleration is kind of a variable. The way the question gets asked itself is rather interesting. They're saying here, find the initial acceleration including the force of gravity. Write Newton's second law. T stands for thrust, and solve for the acceleration. Okay. Well, this is the thrust that is being provided. And if there's no gravity, all of that thrust will go into giving the rocket an acceleration without any gravity hampering that acceleration. But if there is acceleration, very interesting. The mass of the rocket at liftoff, they said, right? That's pretty important. Mass of the rocket initially times the acceleration that it initially has is going to be equal to the thrust. They told us to use T for thrust. The thrust, we can use T. They're using T, I'm going to use T. The thrust minus the force of gravity. Minus the force of gravity that's on it initially. Now look how they asked the question, guys. Find the initial acceleration. Find the initial acceleration, including the gravity force. The initial acceleration is when the thing is all loaded up. It ain't the acceleration at the end. Divide by mi on each side. Thrust divided by mi is the acceleration provided by the rocket. Take the mi and go here and go here. Mi goes into mi one time. True. True story. What's the thrust? Thrust is a lot of stuff, guys. Thrust is a constant. Why is it a constant? Because VE times ln of the ratio mi over mf where MI and MF are locked in. This is the initial, this is the final. Okay, so what? Well, what's going on here? Well, we already, hey, look, this song and dance we've already done. Yeah, I know. I was the fool that thought he could do it in his head. Sometimes I can, other times I cannot. This time it didn't happen, but we got the answer at the end of it. At the end of the day, we got the right answer. We know what we did. We already got this. This is 1.6875 times 10 to the 6th divided by 1.00 times 10 to the 5th. Really? Yeah, let's try it again. This is this whole thing, we did the whole song and dance earlier right here. This whole thing is 1.6875 times 10 to the 6th. This is 1.00 times 10 to the 5th. The answer at the end of all that is 1.6 times 1.6875. 1.6875 times 10 to the 1, which is 16, minus this. They got 1.69. We're not gonna. I'm gonna see how they wrote that when they actually do it. When you do this, you got 7.075. Guess that rounds off to 7.1. My guess is, let's look over there. They got 7.1 meters per second per second. Typically, the way I enable online exams is I don't worry. Sometimes they might ask us significant figures and we'll answer it. Typically, I don't. You've got more than enough to deal with. I need you to know how to do this stuff. Know the concepts, know how to do this stuff, and I can, there's a degree of flexibility, but you do got to be as accurate as possible if I'm not holding you accountable to the significant figures. I said at the end of the day, either one's going to work. Personally, if I was doing an online exam, if I'm doing an online exam and I'm not being held accountable for significant figures, that's where I would go. I got a feeling the book went here, and there's nothing wrong with that either. But if I'm not holding you accountable to significant figures and there's only, let's say, a 2% error tolerance, probably answer it like that. What are they given? And they're given 7.10 meters per second per second. Okay. I'd go with that. If they weren't holding me accountable to if they weren't holding significant figures, if significant figures are not being taken into account, give as accurate of an answer as you can. Stay with that, not that. If they're not, especially when you're taking an exam because of the error tolerance that's there. If I'm not calling you on significant figures, stay with that. But either one is fine right now. Is this concept okay? Yeah. Initially, that's the acceleration. Yeah, that's interesting in its own right. That's initially the acceleration. Absolutely. Yeah, if you have 100,000 here and 10,000 here, 100,000 kilograms divided by 100,000 kilograms divided by 10,000 kilograms is 10. 100,000 kilograms divided by 10,000 kilograms is 10. ln of 10 times 4,500, get an answer, then divide that. 10 times that, then divide that by the initial, which is 100,000. So a pretty interesting question in that regard. The way this all played out. Let me just make sure. There has to be there's one thing missing, guys. Divided by so the change in that is definitely the thrust. The MDT VE, okay. Let's see what we got here. The thrust, you guys, forgive me here on this one, guys. The thrust is mass initial right. Over the time frame that was there. So okay, let's back up. This is correct. All of this is correct. I just approached it wrong up here. Stay right here. Here's thrust. The thrust is initial delta VR delta T over, because you divided, you basically had this. So you have A is equal to, the thrust is MI delta VR delta T over MI minus G. Yeah, that's true. There's a problem here. It's really, really hard. I mean, the way this is set up, at this instant, what is the change in velocity at that instant? And how fast did that change in velocity take place? This becomes a calculus problem. It becomes delta VR, the delta VR over delta T becomes dV dt. Delta VR over delta T is dVr dt. True. Can't really do anything about it. What I can do about it, however, is we know this is a constant. We know that's a constant for the thrust. So there's a bunch of ways you could go here. Let me write this, and then let me write this. Is there another way to write that? That's a constant, isn't it? Delta M over delta T VE is equal to this guy. These are, this is going to be, this product, even though it arises with a whole bunch of stuff changing, this keeps getting smaller and that keeps getting bigger, but they do it proportional to one another, inversely proportional to one another. So when you multiply them, you still get a constant. And this definitely is a constant. Delta M over delta T is a constant. VE is a constant. That's going to be a constant. This product is a constant too, but it's a weird way it's a constant. It's a constant in the sense that M gets smaller. When M gets half as big as it was, this will be double as big as it was. And they're inversely proportional to each other, so you're always going to get a constant answer. Well, I can't really do much here. Short of an argument with calculus, and even then, I likely need more. I mean, I could figure this out. That's true, but if M delta V over delta T, if M delta V over delta T is equal to what I have over there, it's also equal to delta M over delta T VE. So let me have enough room here, you guys. These are the answers. Remember them. We wrote them down. I think I spoke it verbally, but I didn't write down the right equations when I did it. That is what it's going to be. Now let's get there. This is delta M delta T VE over MI. This is where it came from, guys, right? I mean, you had, when you did this, we had this. The acceleration of the rocket at its initial mass is equal to the thrust, forgive me, the acceleration of the rocket at its initial mass times its initial mass is the net force that the rocket is experiencing. The acceleration of the rocket at its initial mass, A, times the mass of the rocket at its initial mass, M times A is the net force that the rocket is experiencing. That is equal to the thrust minus the weight of the rocket. Very important. It's equal to the thrust minus the weight of the rocket. Okay? So what you're going to do is, if you divide by big M sub I on each side, you got this, you got this. This is the thrust. Okay? So the MI went into MIG, G times. The MI went into T, T over MI. We got this here, we got that there. Well, you remember this one. Delta M was 100,000 kilograms of initial mass minus what the mass was finally, which was only 10,000 kilograms. 100,000 kilograms minus 100,000 kilograms minus 10,000 kilograms is 90,000 kilograms. It happened over 4 minutes, which is 240 seconds. So it's 90,000 divided by 240 seconds. 100,000 kilograms minus 10,000 kilograms, 90,000 kilograms is what we have here, divided by 4 minutes, which is 240 seconds, times 4,500 meters per second. 90,000 kilograms divided by 240 seconds times 4,500 meters per second is the 1.6875 times 10 to the 6th newtons divided by this guy. That's the initial, minus 9.8. Minus 9.8. If you guys can see that okay, I'll try to make it. We'll write it down. We'll come back and talk about, at least write them all down so we have it in front of us. That's going to be the acceleration. The acceleration with gravity, and that's the right way to do it because you're in a gravitational field, is the thrust, which is 1.6875 times 10 to the 6th, that's the thrust, divided by the initial mass, minus G. What do you got? You got 1.6875 times 10. 10 to the 5th goes into 10 to the 6th 10 times. 10 times 1.6875 they're not calling you, if they're not asking for significant figures, go as accurate as you can. Just give the flat out numbers like you're doing a math problem. I already said that. So you got to here. They got it like this. We're not going to, that's, I think they put a 0 here as well. Okay. The big thing is, wow, gravity does take its toll, man. Because if the gravity wasn't there, this is the acceleration you're looking at in deep space, you guys. 16.875 meters per second. If there's no gravity pulling on you. You could accelerate with the thrust that we told you is present, you could accelerate with 16.875. 16.875 meters per second. The way they rounded off, 16.9 meters per second. If there's no gravitational field. If there is a gravitational field, only this much you're going to accelerate. Man, you lost a lot. And that's what they're saying here. So they're given those two. Okay. One or the other, depending on what you're being asked, how you're being asked to take something. They want you to be if they're not really holding you down on this thing, just do it a straight out math problem as accurately as you can, is the advice I give, if they're not going to call you on significant figures on an exam. All right. That's it. This, and we already and we knew that. We had already been given this guy for the thrust. What was the thrust? Thrust is this. This one's just a hard one to get, you guys. How on earth am I going to get? This is true. This right here, you guys, this right here will give me 1,687,500 newtons of thrust. Yeah, and this guy right here, right? Sure. I just can't find the initial acceleration that easily because I don't really know the change in speed. And if I do know the change, I know the change, but not for a short period of time. I don't know the function associated with the change in speed over a certain period of time. I need to find at that instant. For me to find, ladies and gentlemen, delta VR over delta T, for me to find delta VR over delta T at an instant, at time t equals 0, I'd need a derivative. I'd need dVdr, not delta VR over delta t. I would need dVr over dt. I would need dv dt. I'd need the derivative of the velocity function. dv dt. dv over dt is what I would need, not delta VR over delta t. So I can't do anything here. I don't see how it's moving, how it's functioning. I can't really get that unless I get a derivative. But I can get this. I can get that, you guys. Because I know that 90,000 kilograms were lost from 100,000 to 10,000. From 100,000 kilograms falling down to 10,000 kilograms of mass, 90,000 kilograms of mass were lost in 4 minutes. That's 240 seconds. And the exhaust speed throughout that process does not change, nor does this rate change. 90,000 kilograms divided by 4 minutes, 90,000 kilograms divided by 4 minutes, which is 240 seconds. 90,000 kilograms divided by 240 seconds times 4,500 meters per second. That much I do know. And that right there got me the 1.6. That got me the 1.6875 times 10 to the 6th newtons. The 1.69 rounded off. The 1.69 times 10 to the 6th newtons. Divided by the initial mass. That'll get me there. That gives me 16 something. 16 something minus 9 something is about 7 something. And there it is. D is the one that I thought was interesting about the whole thing. Estimate the speed at burnout when gravity is not neglected. I know what the speed at burnout was. Remember, we did it for A. When gravity was neglected, we had a big speed there. Find the approximate loss of speed due to gravity and then get the result. So find the speed at burnout when gravity is not neglected. Now, you can do this without calculus and get it there. So I don't know. I'm leaving this stuff up there. The more I leave it up there, eventually I could probably erase it. Let me kind of wait a bit. I mean, we've got this. I think we've done this. Let's. I think I probably could take that off, you guys. If I need to rewrite it, we can always rewrite it. That's not going to be a problem. All right, let's see here. They're saying, please tell me the speed at burnout if you're not neglecting gravity. In other words, you are accounting for gravity in this whole process, and then you're going to tell me the speed at burnout when you do so. Okay. So what are we talking about in this rocket problem, I guess, so to speak, up to this point, and then just kind of we'll see what we can say. Let's just kind of summarize it a little bit, how we got to here for the rocket problem in the Survey, book. So. In the Survey book that we're talking about, okay, some of the stuff we said on it. So we got the rocket problem there, guys. Just kind of, okay, as we said if you took the whole thing there, there's a whole lot you could say here. I want to just be kind of careful how I say it. We saw, we played the game for this one, and we said that the VF, if there's no gravity under consideration, was coming out like this. Forgive the repetition on this, guys. I think it's just good to see this stuff again. You kind of it's easy to do a misstep otherwise. I think I've seen that. I mean, we all experience it sometimes, so it can happen. Initially at takeoff, the velocity initial is 0. VE is 4,500 meters per second. ln of the ratio 100,000 divided by 10,000 is 10. ln of 10 times 4,500 plus 0 will give you the VF. That comes out, this logarithm here comes out to a number, the natural logarithm of 10, remember the 100,000 divided by 10,000 is 10. Natural logarithm of 10 is a number bigger than 2. So it's going to be more than double 4,500. And it comes out to 10,400 meters per second. Okay, and they write it, and it can all be written a whole bunch of different ways and stuff when we're doing it. VF is 1.04 4 times 10 to the 4th meters per second. Either way, you're good. Okay. That's that. B, the easiest way to have looked at the thrust, you guys, is simply to have said this. The thrust is the mass times delta V rocket over delta T, depending where you are. Yeah, I know, but we did enough mathematics earlier. We found that to be the same as, in terms of magnitude. If there's a problem with the signs, the absolute value is what it is. Just get absolute values, set absolute values equal to each other. You got delta M over delta T. Well, we've been down this road. In fact, I tried to show off earlier doing something in my mind, and it got me nowhere, right? So now we know where the answer is, at least, right? What is delta M over delta T? It lost from 100,000 kilograms, it went down to 10,000 kilograms. It lost 90,000 kilograms. It did it in 4 minutes, which is 240 seconds. The exhaust velocity does not change throughout the process. It's going 4,500, right? So basically, it was this that we were talking about. The VE was 4,500. This is 90,000. Divided by 4 minutes. 4 minutes is 240 seconds. And I am not going to try to show off again. That did not work out well. At the end of the day, you guys, you did get this. So that's the newtons. 1.69 if you want, that's fine too. Depending how you're being asked depending on what the question is, how it's being asked, right? Obviously. Okay. Approximately equal to. If they're not specifying significant figures, you solve it like you're solving a math problem. Be as accurate as you can be. Okay. So that's that for B. For C, that thrust is a constant, guys. They said, look, the force initially experienced by the rocket is the mass initial of the rocket times the acceleration that it is initially experiencing. The force initially experienced by the rocket is mass times acceleration. Its initial mass times its initial acceleration. That's equal to the thrust that the rocket is generating. Yeah, but not so fast. Now you have to account for gravity. And gravity is trying to stop him. Gravity is fighting him by this amount, and the thrust is the takeoff. The gravity is the down-to-earth thing. This thing's pulling it down to earth, the gravity is. This guy's trying to get away from Earth, and that's where you're trying to go. When you do that, you got T for thrust, divide by MI on each side. That simply just distributes. Divide by MI on each side. The thrust, which is a constant, divided by MI. MI, later on, the mass is different. It goes from 100,000 kilograms to 10,000 kilograms in a continuous fashion. These cancel. What's going on here? The thrust is 1.6875 times 10 to the 6th divided by 1 times 10 to the 5th. That's how many kilograms are present initially. Minus 9.8. What we got here? 7.075, right? Let me see what we got here. Yeah, right. 16.8. Right. 7.075. Yeah, I mean, there it is. At the end of the day, A equals I want to make sure this stuff's visible to you guys. It should be okay. I write pretty big. 7.075 and there you go, which is approximately equal to 7.10 or 7 point. Not a heck of a big difference. Again, the way I construct the exams, I don't hold you accountable for significant figures. So the accuracy, as far as like doing it like a straight out math problem, becomes really important because there might only be a 2% margin of error. So you want to do it as far as you can, unless they ask you to do otherwise. At the end, they might ask you, please round it. What is this rounded? Still, do it as accurately, every bit as accurately as possible. And in the end, if they ask for a round off, go ahead and do so. Okay. But that's all this stuff right here. Okay, that's great. How fast is this thing going? I can get all four of them now on here. Okay. So we got A right here. We got B, it's the thrust right here, and we got C, either one of these. I'll tell you how to do it. Why don't you take how fast this thing would have gone if there was no gravity at the end of the 4 minutes? We already found that out. We said it was going 10,400 meters per second. It was going 1.04 times 10 to the fourth meters per second. 10,400 meters per second is how fast it will be going at the end of 4 minutes of firing that rocket if there's no gravity fighting it. The problem is it's not how it works. There's an acceleration associated with it. Continuously, there's an acceleration associated with it. So you could, here's where it gets very, very interesting. Some people are wondering, are thinking, it's very easy to be careless this way. I'm careless more than enough times. We all are sometimes. Some people are thinking, 7.075 meters per second. Why don't you start that at t equals 0 seconds and take it for 4 minutes? 240 seconds. 240 seconds of that kind of acceleration. Don't do it. It doesn't work. 240 seconds of this kind of acceleration makes you kind of wonder, would it work? It doesn't work. Why not? Because you guys remember way back, didn't I say the thrust is a constant force as long as the rockets are firing, expelling mass at a constant rate, delta M divided by delta T. If delta M divided by delta T is a constant, what do you mean? 90,000 kilograms, because it went from 100,000 kilograms to 10,000 kilograms. 90,000 kilograms lost in 240 seconds. Delta M divided by delta T is a constant. VE, the velocity of the exhaust in terms of magnitude, is also a constant. A constant times a constant is another constant. Well, true, a constant times a constant is another constant, and delta M divided by delta T remember, don't want to write it here. I already wrote it down. I'll write it here. We know that delta M divided by delta T times VE, that's equal to, not I, that's equal to M mass times acceleration, which is delta VR over delta T equals force thrust. Sure. This keeps varying, and so does this. This keeps varying, and this keeps varying, but their product is always a constant, and it's going to be equal to this. I already said that a number of times. It's important enough, we can't forget it. We got to know it. All right, true. So you're telling me 90,000 kilograms divided by 240 seconds times 4,500 meters per second is going to give me the 1.6875 times 10 to the 6 newtons. The 1,687,500 newtons. Yes, that's what I'm saying. If you divide it by the mass of the rocket on the launch pad, you'll get this acceleration initially. That mass on the launch pad occurs only on the launch pad. It loses mass as you go up. If it loses mass as you're going up, the acceleration goes up. The acceleration changes. You just can't say, oh, hey, Bayless, it started at 0, here's the acceleration. Take the acceleration and multiply it by 240 seconds, 4 minutes. Multiply the 7.075, multiply that by 240 seconds, which is 4 minutes. This acceleration is a one-shot deal. That's why we were in trouble to begin with. We needed not a delta VR over a delta, we did not need a delta VR over a delta T. We needed a dVR dt. We needed a calculus problem if we were going to go that route. We get away with not needing to go the calculus route by looking at this, ladies and gentlemen. By looking at this. That's constant times constant answer. This varies, so does that, but they're inversely proportional to each other, so you're always getting a constant. It's a big thing. Okay, great. I can't use this. What can I use? Tell you what I'm going to do. Let's take the velocity. Let's take the velocity that this guy would have attained, this rocket ship. Let's take the velocity that the rocket ship would have attained in terms of magnitude, which would be 10,400 meters per second. 10,400 meters per second. That's what it would have attained if it didn't have gravity fighting it. Gravity's going to fight it. Gravity's going to fight it for 4 minutes. That's the ticket. That's how we get out of there. That's how we get it. Because if the thing was going real fast up there, that's what it would have done. It's a rough one. I mean, let's just do it. I think if this is easier, as I often say, it's easier done than said. Tell you what I'm going to do. There's a number of ways to go here. They explain it in a particular way. I'm going to explain it my way. Let's find V associated with G. I don't know how to do this. Let's go VF. Let's just call it V. Let me see what I had over here. I had VF over here. So let me use the same language here, guys. Let me call V the V after 240 seconds, but gravity's fighting you. What's the V after 240 seconds with gravity fighting you? What do you say you take VF, which is what it would have been, and minus GT. Watch this. This guy's 10,400 meters per second minus 9.8. I'm going to talk to you about that in a second, why that's true, but we'll see. All right. This guy is being decelerated. This acceleration is working on the rocket whether the rocket knows it or not. It's working on it at a rate of 9.8 meters per second, and it's doing it for 240 seconds. Let me see if I'm agreeing with the book, you guys. Yeah. Still moving. I mean, there's no point in a rocket if it ain't going to work, you guys. It's still moving. It's still moving up. Don't ever get that out of your mind. There it is. 8.048 or 8.05 times 10 to the third meters per second. I just like to say 8,048 meters per second. They got 8.05 times 10 to the third meters per second. I know this would have been my speed had gravity not intervened. If there was no gravity, that's my speed at the end of the day, you guys. This is my speed at the end of the day if there's no gravity. Because there's gravity, working with this guy, whether you know it or not, there's an acceleration, decelerate. This guy's the brakes. This guy's the brakes. This guy's the brakes. For 240 seconds, he's the brakes. How far was he slowed down? That much. 8.048 times 10 to the third meters per second. They wrote down 8.05 times 10 to the third meters per second. 8.05. That's not a big deal. Because of the symmetry. That's crazy. You would get this kind of VF. You know when you'd get it? If you added a GT on each side. VF, the fall down. It would, let's say there was the rocket was empty. There's an experiment going on. They got things in the rocket. They want to experiment with what happens with the collision and stuff like that. Okay, so they go far away and they let it fall down and they do an experiment. What's the VF going to be at the bottom if it's only going V amount at the top? Why don't you add a positive GT? Why don't you add a positive GT on each side? If it's falling down, this guy adds the speed to it. If you're only going 8,048 meters, you're only going 8 kilometers per second, guys. What are you doing? You know, it's nothing. It's only like 5 miles per second. What's the big deal, right? Right? It's about 5 miles per second, literally. That's something else in its own right, right? At that rate, in 20 seconds, you're in Chicago. If you're going 100 miles. You're going 100 miles in 5 seconds. What would the VF be? Well, if you're only going 8,048 meters per second, and for 240 seconds, you got G helping you come down. When you do come down, you're going to be going at 10,400. You're going to be going at 10,400 meters per second. That's crazy. Well, D was interesting. The reason, now D, we got out of the woods. We got out of the woods okay. We just couldn't get out of the woods doing this guy. We couldn't do it here. regarding what you got there, you guys. You just couldn't do it. You couldn't take the seconds and figure out what the average was. I mean, in other words, we're not saying, let me just try to, for some reason I'm looking at this thing. Let me just do one more thing here. Everything we just said is correct, period. That ends the story, actually, is what it does. Yeah, it don't work, guys. I mean, the other way, and this is all correct. There's nothing wrong. Nothing wrong. If you said, hey, look, Melis, I'd like to just go. I'm going to erase this really quick. I'd like to say, hey, you know what? The V is going to be some kind of V initial plus AT. I'm going to agree with you, but in a conditional way, I'm going to agree with you. This is the initial acceleration of the rocket when it's all loaded up, having a total mass of 100,000 kilograms. That's its initial acceleration. After it has jettisoned 50% of its mass, and it's half as massive as it was before, the acceleration will be twice as big. The acceleration will be twice as big. When this guy, well, I take that back. Let me take that back as well. The acceleration independent. Forget about gravity. Then the acceleration independent of gravity is going to be, it's going to be more. In other words, if it was an acceleration of 10 meters per second, 10 meters per second, when there was a mass of 100,000 kilograms total associated with the rocket, when half the mass is lost, then the mass that remains is half as much mass. It'll be double the 10 meters per second. It'll be 20 meters per second for the acceleration independent of gravity if that happens. You can't use this. It's not going to let you. When I multiplied this guy, the 7.10 meters per second, or actually I multiplied this one. I took the 7.075 meters per second, 7.075 meters per second, and I multiplied it with 240. I took this and multiplied it by 240. I got about 1,700. I got about 1698. I got about 1,698, about 1,700 meters per second. Is how fast it's going after 240 seconds. You know it's not going 1,000. It's not going 1,700 meters. It's not going 1,700 meters per second at the end of 240 seconds. It's going almost 5 times that. It's going 8,048 meters per second. Why did I get such a small number? Because this acceleration is really small because the rocket is all loaded up in the beginning. I can't give you a good acceleration for the force that I can put into it. I can give it a great force, but it's so massive I can't give it a great acceleration. When it loses a lot of mass with that same exact force, of 1.69 times 10 to the 6 newtons, with that same exact force, if the mass is 1/3 of what it was, I can give you a great acceleration. And that great acceleration will help it reach 8,048 meters per second. It's not going to go to 1,700 meters per second. That would only happen if that's still fast, if that was the constant acceleration. It's not. It constantly varies. Because it varies, you got to find what the average acceleration is. We got to find what the average acceleration is to do that. And that's a calculus problem. It's the mean value theorem that'll get you there. It's the mean value theorem that'll get us there, you guys. So, with that in mind, For that one right there, for that rocket problem. Let's start it. And now remember what the answer is. It's this. Remember what it said here in the book. I'm going to get an average acceleration bigger than that. Heck. Tell you what. We got this far, we got this far. See that right there? Why don't you divide that? Remember now, didn't it start at 0? Didn't it start at 0? Yeah, it started at 0, and then gravity beat it up pretty good. It started at 0. For 240 seconds, I'll give you the average acceleration. Isn't acceleration change in velocity divided by change in time? At time t equals 0, there's no speed. At time t equals 240 seconds, it's 8,048 meters per second. Let me take 8,000. Let me take, for an average acceleration, total, and that's with, this is what gravity now. This is what gravity. So we keep in the back of our mind. This is 8,048 meters per second minus starting from 0. Time t equals 0 seconds to 240 seconds. This is meters per second divided by seconds. It's going to give me what I want. Okay. I'd like not to erase any of the stuff a lot of times, guys. It's just we run out of it. Luckily, we got it on film so we can kind of look at it. What's going on here? Average acceleration is the change in velocity over the change in time. Now, this is what gravity now. This is what gravity. It started at 0 and it got up to 8,048. We discovered that. 8,048 meters per second. It did it, ladies and gentlemen, in 4 minutes. It did it in 4 minutes, which is 240 seconds. The reason this guy gave me a bad answer, the 7.10 meters per second gave me a bad answer because when I multiplied 7.10, or this one, I can't remember, I think I used this one, a little more accurate one, whatever that means, right? The 7.075 meters, the 7.075 meters per second, the 7.075 meters per second multiplied by 240 seconds got me about 1,700. Roughly, use either one, no big deal. We're not going to split too many hairs on this one at this point, just discovering this stuff, guys. It's about 7.1 meters per second. Initially, with that really massive ship that's got to go up. Well, it's a lot of mass. You're not going to get a great acceleration. When it loses a lot of that mass, the acceleration will go up because the thrust remains the same. The thrust is 1.6875 times 10 to the 6th. 1,687,500 newtons. 1.6875 newtons, 1.6875 times 10 to the 6 newtons. 1.67 million, 1.69 million newton. The thrust will stay the same. The acceleration will go up when you lose a lot of mass. The product of mass and acceleration will stay here. 1.69 times 10 to the negative, 1.69 times 10 to the positive 6th, or 1.6875 times 10 to the 6th newton. It will always be one of those. It'll always be this. Let's just say they're the same. It'll be, let's use this one. It'll be 1.69 times 10 to the 6 newtons, mass times acceleration. If you lose a lot of mass, there's a small amount of mass left over, but the acceleration proportionally goes up. So when you multiply mass times acceleration, you'll always get that answer. Well, I took the thrust and I divided it by I took the thrust, you guys, of 1.69 times 10 to the 6 newtons, and I divided it
by 1,000, I took the thrust of 1.69 times 10 to the 6 newtons, and I divided it by 1 times 10 to the 5th kilograms. 1,690,000 newtons divided by 100,000 kilograms got me 7.10. Well, it didn't get me, it got me 16 something, minus 9.8 got me down to here. So there's a lot going on, you guys. What's the average acceleration? That's a lot. It's an awful lot. I mean, yeah, sure is. Just, yeah, at the end of the day, so let's see here. There's got to be something here that's not what I want it to be. They're giving a pretty big number here. I mean, at the end of the day, you guys, and I don't want to believe it, but I tell you what, I'm kind of doing this kind of almost brand new on this thing. That one I'm throwing the dice on it, but let's throw the dice. Yeah, I mean, it doesn't lie, man. It's just an awfully huge number, guys. Just trying to see if I made a mistake here. I don't think that I did. This is 8,048. This is a difference in velocity of 8,048 meters per second divided by 240 seconds. Okay, you're going to, I don't know, you're going to, at least I almost fell over when I saw this, but I'm getting this. Yeah, that's the average acceleration. It's even bigger in some other places, smaller in others. That's the average acceleration even with gravity fighting him. Even with gravity fighting him. You got to be kidding me. Yeah, no, I'm not. Yeah, it's and if it's that's with gravity. That's with gravity. Acceleration without G. What do you think that would be? I wish I had a class in front of me. We could talk right now, right? We talk about it. What do you think that would be? If this is the acceleration while you're fighting 9.8, if this is the acceleration while you're fighting 9.8 meters per second, imagine if you weren't fighting 9.8 meters per second. This is what it is when you're fighting 9.8 meters per second. You have already had 9.8 meters per second taken away from you. You had 9.8 meters per second of ability to accelerate. 9.8 meters per second of that ability has been taken away from you. What if it's given back to you? If it's taken away from you, you got this. Give it back to you. Why don't you add 9.8 onto here? You add 9.8 onto here. Last time I tried to do something in my head, it did not go right. This one will, I think. I'll show you. The 0.8 onto this guy is going to give a 0.3, 42. Man, that's some kind of acceleration. Some kind of acceleration. Let's make sure it's true, in case I did something foolish again. Yeah. And I did. It's even more impressive, guys. 43. 43.333 going on forever, basically. Are you kidding me? Just erase this a little bit. Are you kidding me? I guess the question to ask is, what would happen if you multiplied that acceleration without gravity, if you multiplied it by 240 seconds? Do you think you'd get this guy? I'd be racing. Do you think you'd get this guy right here? The 1.04 times 10 to the fourth meters per second. Do you think you'd get 10,400? 10,400 meters per second is what speed you would attain if you did not have to fight gravity. If you do have to fight gravity, you can only get to 8,048 meters per second after 240 seconds. But if you don't have to fight gravity, after 240 seconds, you can reach 1.04 times 10 to the fourth meters per second. You can reach 10,400. I guess if I take this guy, the 43.3 times 240, sure enough, 10,400. That's crazy acceleration due to gravity. That's crazy. I'm sorry, that's crazy acceleration without gravity due just to the thrust of the rocket. And this is still crazy acceleration even when gravity's pulling you down. They're off by about 10. By about 10 meters per second per second. You multiply this by 240 seconds, you'll get 8,048 meters per second. You multiply, that's because you're fighting. If you're fighting gravity, this is the best acceleration I can give you. You multiply this, this is the average acceleration, guy. This acceleration occurs somewhere, but look where it started, man. Man, you started at about 7.10. The initial acceleration due to gravity is only 7.10 meters per second per second. How on earth are you saying that this is the average? This is the initial acceleration. This is the initial acceleration when you account for gravity right at liftoff. 7.10 meters per second per second. 7.10. That's right at the beginning. I'm saying the average acceleration for the flight. So this, as we said, this is with gravity taken into account, 7.10 meters per second, right at liftoff. That's the acceleration. The average, however, is a lot more. It's like, somewhere between 4 and 5 times more than that. Between 4 and 5 times more than that is really what the average is to get out there. Why? Because it keeps losing weight. It keeps losing mass. It keeps, not weight, mass is a better word. It keeps losing mass. And as it loses mass, its acceleration goes up. There's going to be a really big acceleration somewhere, bigger than this. And there's a real small acceleration which is equal to that. So that's pretty important stuff. Okay, so let me just check here. All right, guys. So as we proceed, I just want to make sure I'm still being recorded pretty well here, guys. All right. Is that crazy? Yeah. It's a lot here. Remember the numbers. Remember the numbers. I guess you could say and I have, like I said, I have this in pretty big detail on Canvas. So let me let's verify this stuff, man. Let's see where this thing is. I think at the end of the day, we said a lot, so let's kind of wind it down, I guess, and get to where we want to go. All right. Let's see what we can do here. I'm going to erase. Remember these numbers now. Remember all the numbers, right? We got all the numbers. On the low end, we got roughly 7.10 meters per second. On the average, we got 30. Now again, look, on the low end, it's actually 16.875. 16.875 meters per second if there's no gravity. 16.875 meters per second squared, 16 point something meters per second squared, almost 17 meters per second squared if there's no gravity accounted for. The average associated with no gravity accounted for is 43.33 meters per second squared. 43.33 meters per second squared is the average acceleration throughout there's high accelerations, a lot higher than this, and low accelerations, which is 16.875 meters per second squared. So about 17 meters per second squared is the low, and then there's a high, and all together, they average to here. You can't average the low and the high on this one because there's a lot of mathematics going on that's not linear. That's why you got to use calculus. But this is on the high side. This is if there is this is the average, if the average acceleration if gravity is not taken into account. The initial acceleration without gravity being taken into account is 16.875 meters per second squared. About 17 meters per second squared. 17 meters per second squared is the amount of acceleration initially present with no gravity being taken into account. 17 meters per second squared. The average acceleration throughout the journey, 240 seconds of the journey, is 43.33 meters per second squared if no gravity is accounted for. If gravity is accounted for, the low end is not almost 17, it's a little more than 7. Yeah, and the average, if you're accounting for gravity, is not 43 point something, it's 33 point something. Okay, just remember those. Let's run through this real quick. See how the whole thing plays out. I just think it's this, and again, a lot of this, notice we did a lot of this without calculus. We did some stuff with calculus to kind of just provide a foundation early on. But afterwards, when we had the formulas, notice all this running around was done without calculus. Certainly it's going to be done without calculus because the book itself, the Survey book, doesn't use calculus on it. But let's see, for our personal enrichment, how this plays out. All right, let me try to run through it. I think we got so much foundation here, guys. I think we're okay. I am going to use kind of a different notation. We will prove the following with this beautiful theorem known as the mean value theorem. It's like a weighted average. You're averaging a function is what you're doing. You're not averaging 5 masses, you're not averaging 5 masses, what the average mass is. You're averaging an infinite amount of masses, actually, and you're using calculus to do that. You're doing a weighted average on a function is what you're doing. Pretty beautiful stuff. Well, this is the final speed of the rocket with gravity fighting it. That's equal to okay, we can do a bunch of stuff here, I guess. We will take VE ln what is going on here? Didn't we say that the final velocity, kind of putting let's look at it. It's not too bad. Shouldn't be too bad. Very, very similar. I mean, I said a lot of stuff, and that kind of makes it hard to follow all the stuff, but you can always go back with the film and stuff, and we can talk a little, you can look at it a little bit more. But is it true that the final velocity due strictly to the rockets firing and expelling all their mass? Remember, you did have 100,000 pounds. I'm sorry, you had 100,000 kilograms of mass. You had 100,000 kilograms of mass initially, and you ended with 10,000 kilograms of mass finally. 100,000 kilograms divided by 10,000 kilograms divided by 10,000 kilograms. 100,000 kilograms divided by 10,000 kilograms is 10. ln of 10 times the 4,500 is the 10,400 meters per second. That will occur without gravity fighting you. Yeah, and then you took 9.8, multiplied it by 240. You get it, guys? We took 100,000 kilograms initially, got down to 10,000 kilograms, divide, you got 10. ln 10 divided by 4,500, ln 10 multiplied with 4,500 rather, and you get 10,400 meters per second. Minus 9.8 times 240. Yeah, we got that. We got that answer. We definitely got that answer. That answer, what did that answer come out? You know what it came out to. 100,000 divided by 10,000, 10, ln 10 times 4,500, that's 10,400 minus 9.8 times 240, it's 8,048 meters per second. Okay, so we got that. We will find the result again using the mean value theorem of calculus, but this will be equal to the average upward acceleration minus the downward acceleration. So it depends how you want to write this thing, I guess you could say. So we got this right here. I'm just trying to argue with myself here. And that's never a good idea. Me arguing with myself, I'm arguing with an idiot, but let me see what I can do. In this case, F thrust is equal to constant, but M and A both vary inversely to one another. Okay, we already talked about that. I could keep it with the symbolism, guys, and we can maybe. I don't want to overwhelm you with this either, to be honest with you. Yeah, we know that. We know that's going to be the end game. Can you get the end game? You know, can you get all this at the very end of the day as the answer. I tell you what, I'm just trying to figure out. I subtracted the G later. I just don't want to. I don't want to do. I want to keep the G. All right, let's do this. This is what we're going to do. I know what they're doing. Let me find this guy right here. This guy right here, that guy right there, is going to be equal to an average acceleration. This guy right here, all of this, is going to be equal to an average acceleration without gravity times time minus, let me just try to, I think when you read my notes, you're going to have an easier go of it, but right now, let me try to walk you through it verbally as best I can. Right? Is that the same as this? Hey, weren't we doing this kind of subtraction earlier? Yeah, that's all true. Interesting. The way you can do it you got to find something here. Now this is, forgive me guys, I guess I could say this. The F thrust, the F thrust function is a constant, and it's equal to m times a, which is equal to m delta v delta t. Yeah, kind of, sort of. Yeah, you're going to have to, this is all changing stuff. The delta m over delta t is this guy right here. Okay. This varies. If you stay here, if you divide by capital M on each side, the acceleration is a variable quantity, even though F thrust is a constant. F thrust may be a constant, but M is constantly changing. It's going from big to small. It's constantly changing. If this goes from big to small number into here is a big answer. So that's true. Is there an average? Yeah, let me see if I can say that. I'll put a bar there to say average, right? I'll say that, equals A average. Equals A average. True. We can say that. Let's talk some more. Is it okay to say this? That A bar equals F thrust F thrust over M, that ratio, average. The average of that ratio. This is a variable quantity. This is a variable quantity. If I somehow get an average of this variable quantity, I have the average I'll have the average acceleration. Let me try to think here. What do you say? There's a lot to be said here. They're telling us this guy's a constant. I already was delivering that speech, right? If you take that's the acceleration, so it's what it's going to be. I need an average on that. Just want to argue this point a little bit, guys. Is it true that F thrust is VE delta, and then they told us this is fine. They told us this is fine. VE delta M delta T. That's F thrust. Divided by M. This is what F thrust is. This thing right here. And that whole thing, the average of that. You're just getting the average of all this, guys. And that's the same as this. Well, this is a constant. This is a constant. So VE delta M over delta T, that's a constant. Yeah, I know, but you're still getting an average here, guys. The M is not a constant. The M is varying. So you got to multiply it by the average of this guy. And that's going to be the A bar for now. You're thinking, what are you doing? Why are you getting an average of 1 over M? Because the 1 over M was the only thing that was varying. The F thrust is a constant. The VE delta M over delta T is equal to F thrust, and that's a constant. That's a constant. The top here is a constant. The top here is equal to the top here. Both of these items are equal to one another. Both numerators are equal to one another, and F thrust is a constant. If it's a constant, only this guy is varying, so I got to worry about this guy varying. And that's the big one. This is kind of the argument as to where it's going to go with the calculus background. Those of you not having calculus, you don't need to go where I'm going right now. But if you don't have calculus, it's a good thing to look. I mean, if you do have calculus, it's a good thing to look at. Look at that over there, you guys. Look at what we got. We said a bunch. Again, I always don't like erasing this stuff, but what is going on? Well, let's keep talking, I guess. The whole question is this: how on earth are you going to find the average? Of that. What is the average of that function? The average of that function is arrived at by a beautiful theorem known as the mean value theorem. you are going to integrate from, and it gets kind of awkward here, I guess you could say. You're going to integrate from a large mass to a small mass. You can do a whole lot of stuff here, guys. From a large mass, Mi, to a big mass, Mf, 1 over m dm. Yeah? And you're going to divide what delta m is. Which is Mf. Look, this is a little on the awkward side in the sense that Mf is small, Mi is big. Small minus big is a negative number. Yeah, I know, but you're going to get a negative number up here. So you're going from big to small. You're going from big to small. You're going to get a negative number here, but small minus big is also, small minus big is also a negative number. Integrate from small to big, get a negative number. Go small minus big, get a negative number. Negative divided by negative is positive. Better way to do it maybe is going MF to MI, get an answer, and then go MI minus MF. You got to get the difference between the two. But this is the crux to the whole thing, you guys. If you do this, you get ln m evaluated between those two limits. ln m evaluated mi mf over mf minus mi. That is going to be ln mf over mi. That's going to be a negative answer. This is a ratio less than 1. It's a positive ratio. It's a positive ratio, but it's less than 1. It's bigger than 0, but less than 1. It's a positive ratio less than 1. The logarithm of a number less than 1, but greater than 0 is a negative number. This is a negative answer. That's also a negative answer. If you switch these, you get the opposite of what this is, and it's going to be a positive answer. The delta m here, to get a positive, if you multiply this by a negative 1 and multiply that by a negative 1, you get all this. This right here is the average of the function 1 over m. Okay, good. If that's the average of that, why don't you, this here is what we had over there, right? So let's see what we got. We can go 1 over m, the average of 1 over m is all this. Mi minus mf is delta m, actually. And we got the acceleration given over there. Acceleration is VE delta m over delta t you got all this, this equals that. Mi minus mf is delta m. Okay. So what we got here is, if it's delta m, cancel that out. And what do we have? We have Well, we got a lot. We've got A is going to be this. You'll see what I mean. Don't want to erase just about anything, guys, but okay, let me erase something. What's going on here? Yeah, I got something for you. I mean, can I talk to you about that? Is that the same as VFG equals VE ln MI MF May I do something here? Let me ask you something here. Did we say that? We said that, VFG equals A bar T minus GT. Okay, and I got down to here. Got down to here. Well, wait a minute. If this is GT, this right here's got to be A bar times T. A bar times T minus GT. A bar times T minus GT. This guy, that's the only way it could happen. This is A bar. Now you're probably wondering, wait a minute. May I say something else, ladies and gentlemen? VE is ln MI over MF. Yeah, the delta M's went. Delta T is on the bottom. Delta T is the change in time from time T equals 0 to time T. Time T minus time T equals 0. T minus 0 is T. That's equal to delta T. Delta T is TF minus TI. We said you start at time T equals 0. You start at time T equals 0 and you go to T. Delta T, ladies and gentlemen, is T. This guy right here is the average acceleration. The delta T is T. Is that true? Yeah. If you multiply by T all the way across. T times G is GT. T times this, distribute the T. T times G, GT. T times all this divided by T. T times all this divided, which is got a T on the bottom. The T's cancel, you got that. Then you're here. This is that's the average acceleration. That's G. Remember the 33 and the 43 that we talked about? It's pretty neat. Remember the 33 and the 43? This is about 43. That's about 10. What's 43 minus about 10? It's about 33. If you don't take 10 away, it's 43. That should be 43. That should be 9.8. This should be 43 just by itself. No gravity, that should be about 43.33. You take 9.8 away, it'll be 33.533. With the minus g, this should be 33.53 meters per second per second. All of this. 240 seconds, right? 240 seconds. And that's how it plays. Just quickly. It's a delta t. I left the delta t on the bottom. Either way it works, guys. That's the essential argument. All that's left is to show it. Yeah, pretty easily, I think. This is the acceleration, no gravity, and a bar is the average acceleration without gravity present. A bar is the average acceleration without gravity present, and a bar minus g is the average acceleration with gravity present. So this guy is average acceleration without gravity present, and this is acceleration of gravity. Average acceleration without gravity is this. It's going to be 43.33. Average acceleration with gravity, subtract the 9.8, it's going to be 33.53. Those are the claims we're making. So, yeah, I believe that's true. What the heck? Let's prove it. Let's prove it. You guys remember, this was 100,000. This was 10,000. 100,000 divided by 10,000 is 10. ln of 10 times 4,500 was 10,400 divided by 240. Divided by 4 minutes, 240 seconds. 240 seconds. 43.33 meters per second per second. Subtract 9.8 from that. This is with gravity. 33.533 meters per second per second. That's where it's coming from. We're even actually getting actual numbers when we're actually doing it. This guy right here is the acceleration times time. This guy right here is also the acceleration times time. The time is hidden, but it's there. Where is it? This is the acceleration times time. Divide it by t, and you got the acceleration right here. Oh, yeah, that's this. Take this divided by t, and I got the acceleration right there. Oh, yeah, that's 43.33 meters per second per second. Divide this, take all of this, and on the outside of it, don't go into the logarithmic function. Stay right here, and on the outside of it, divide by t. That's acceleration. Then, if you multiply by t over here, here's the acceleration. The t's on the bottom. Okay, guys, it's done. I have it on Canvas as well, fully worked out. The survey book's got good coverage of it, but there's some subtleties that aren't really discussed in the survey book. And that's not, there's other things that they discuss that I don't discuss. I mean, they discuss a tremendous amount. I mean, they do a great job. If they were going to discuss every single subtlety, you guys, the book would not be this thick. It would be that thick. So it's perfectly understandable. It's a great book. We're lucky to have that book. They discussed every subtlety. Like I said, the book would be that thick. No book does that. Nobody does that. The stuff I write, I can't do that. Nobody can do that. So have fun with the stuff, guys. Look at it. Very interesting. Thank you. Thank you for your time.